Hello everyone, I'm Germán Barquero. I'm here to present our latest work will be presented in ICCV 23 in Paris that is called BeLFusion, Latent Diffusion for Behavior-Driven Human Motion Prediction, which is a work joined with Sergio Escalera and Cristina Palmero. This work focuses on the problem of human motion prediction, which is given an observation of a motion, we want to predict how this motion will continue in the future. But we do it from a generative point of view, that is, we predict n predictions that will be equally plausible given this contextual scenario. Prior works have focused on showing how diverse the predictions are by plotting at the 2 seconds mark how these poses are by overlaying them, but we show that they have been missing an important point, which is how this diversity evolves in the future. And we showed that because of that, they are having very fast transitions in very low amounts of time. And we can see this by plotting the average velocity of their joints in the future, and we see how very early they start predicting very fast motion that moves the predictions towards very diverse poses, which of course maximizes the diversity metrics. Our contributions in this work are: first, we propose BeLFusion, which is a combination of latent diffusion models and behavioral disentanglement of the latent space for more realistic and coherent predictions. We also propose a new cross-dataset benchmark for stochastic human motion predictions. And finally, we propose 2 metrics that show are significantly correlated to realism, CMD, and average pairwise distance error. BeLFusion consists of 2 very different processes. First, the behavioral latent space generation, which is generated by putting 2 decoders into a fight, into an adversarial interplay, which eventually, by giving access to different information and alternating these losses, the adversarial interplay leads to a bottleneck that eventually disentangles behavior from motion. This allows us to transfer any behavior to any ongoing motion. In this GIF, we see how this pendulum behavior is transferred to any ongoing motion by adapting this performance to the given context. Now, in the second stage, BeLFusion, what it does is, okay, we want to predict, given this observation, we want to use latent diffusion models to transform, to decode a Gaussian code into a behavioral code inside this behavioral latent space, so that the behavioral coupler is able to transfer this behavioral code into the following the continuous motion into the future. So what's cool about this, using diffusion models for this, is that we can apply losses in 2 different spaces. Here we can apply the loss in the behavioral space. We can ensure that the behavioral code that we predict is the same as the behavioral code of the actual ground truth. We can do that also for the reconstruction loss in the original joint space. By applying an implicit diversity loss, we argue later that we can increase the diversity of these predictions by increasing k, which is how many predictions we predict, and out of these k predictions we only backpropagate in 1 of them. So the results show that our method excels at accuracy and also in the diversity adaptation to the context. What does that mean? That if we analyze which is the average pairwise distance or the diversity metric for the ground truth in each of the classes of the human 3.6 dataset, we see how this diversity oscillates and changes depending on the class. And our method predicts motion that keeps this oscillation and matches very well this diversity to the context. We also show how the implicit diversity loss that we showed promotes diversity and accuracy. The higher the k value is, the better the diversity and accuracy are. And that also going through all the denoising steps boosts realism and diversity. Finally, if we show these visual results, we see how our method predicts progressive and realistic diversity, and also it adapts better to the context. Here the person is eating, so that the person will not go pick something on the ground, even though that is the motion that maximizes diversity. It also predicts smooth and realistic transitioning. Here, for example, it is transitioning better than the state-of-the-art methods that are simply moving to very distant poses. Here, in this case, this is in an example of the cross dataset scenario in which this movement has never been seen at training time. All the other methods at predicting memorized examples or memorized motion from the training set, while our method is able to successfully learn or predict the motion dynamics that will follow this observed movement. So thank you for listening. Our code and pre-trained models are available for use in our GitHub. Thank you.